Hello everyone, it's Aaron here. Welcome to my video on analyzing electronic circuits. Now, before we proceed to the actual review, I want to go back to Unit 1 first and tackle these dependent current sources. So when we're doing an analysis here, generally we want to identify these values first. Alright, I'm going to update the circuit. To get I, it's simply Ohm's law, so that's 10 over 2, so that's 5 amperes. And since this is requesting 4I, so that's going to be 5 times 4, right? So 20 amperes. I can just simply update this to be 20 amperes. Now, if I'm going to do nodal analysis here, that should be plus 20 plus VO over 1 ohm is equal to 0. This implies that VO in this case is going to be negative 20 volts. Oops, negative 20 volts. Now, let's say instead of depending on the current of I, we're going to change this to voltage. So it's going to be 4V. Now, we're just going to base it on the voltage of this. And since it's in parallel, the voltage is shared. So this 10 volts is now here. But it's asking for 4V. So 4V is going to be 4 times 10, so that's 40 volts. I can simply replace this to a value of 40 amperes, right? And when I do a nodal analysis again, it's going to imply that VO, when we are depending on the voltage instead, is going to be negative 40 volts, right? So that's about it for dependent current source review. Beginning Unit 2, it's going to start with diode analysis. There is no correct way to do circuit analysis. The main gist is we do a guess, and then we just validate if it's correct. If it's wrong, we just start again. There's nothing wrong with starting again. To demonstrate, I'm gonna start with a cutoff analysis. This is wrong, but I'll just show you how fast it is to recover. Assuming this is cut off, we have 5 volts here, right? And this is gonna be ground voltage. So there is a huge gap here. That's gonna imply that there's no current that can flow. Again, electrons cannot just jump out of thin air. They need to have a valid path. And when this is 0 amperes by Ohm's law, 0 amperes updates this. So there is 0 volts across this resistor here. There's going to be no voltage drop. That means this is 5 volts. Now that is a contradiction because for cutoff to work, the voltage must be less than 0.7. But we have solved 5 volts here. So cutoff was wrong. And now we are going to restart and assume that our diode is going to be operating. So we just write down our model again. That's 5, 1K. I'm gonna replace this with 0.7, sorry. Replacing this with 0.7. Now to validate if it's on, we just check its current. This is gonna be, by Ohm's law again, 5 minus 0.7 over 1K, that's gonna be 4.3. And then this K will make this milliamperes. Now this is obviously greater than 0. So it's a positive current, which means that on is allowed. This is the correct circuit, this is the wrong circuit. And that implies that since this is just VD, or sorry, this is V out. Our V out here is going to be 0.7. So it's a very fast type of analysis. The general gist when we are doing analysis for diodes, this is the model of a diode by the way. It has the plus and minus like this, and the current flows this way. Diodes have two states, the off state and the on state. And to verify, in the on state we have a voltage source, right? And we need to check if its current is positive. So we check if this is positive. If this is true, then we are in the on state. Now, let's say it went the other way around. We need to flip to the off state. In the off state, we have a 0 amperes of current here because of this gap. Since the current is already given, we're just going to check its voltage. If this voltage is less than the activating voltage, this is usually 0.7, then the off state is valid. Otherwise, you need to go to the on state. That's about it for the general checks for diode analysis. Okay, now when we are proceeding with more diodes, the trickiness here is it's an exponential type of analysis. When you have one diode, you just check 2 states. But when you have if you have 2 diodes, it's going to be 4. If it's 3 diodes, it's going to be 8 and then 16. So when you get more and more diodes, the number of possible combinations to verify is going to be exponentially larger. What's a good starting point? Start anywhere. Let's say we go with both of them being off. Let's say we have D2 and D1 here, and here is our check. 0001, 1011. 1 represents it's on, 0 represents it's off. Let's say this is gonna be D1. This is D1, this is D2. If both of them are off, let's just disprove if this is gonna be wrong. This is 3K, but since there is no current flowing through here, that's 0 volts. So this is ground voltage. And then you have a 10 here. Now this 10 volts here is clearly greater than 2, so this is supposed to be on. As long as one of them is already wrong, the entire circuit is wrong, okay? So this is not going to be the correct case. We've disproved this. Now, I'm going to skip a lot of these analysis steps and I'm going to go to the correct answer for the sake of time. There's always only one correct answer. Let's say this is D2, which is this one. Let's turn D2 on. D2 has a voltage of 2, and this is 10. 3K, blah, blah, blah. So 10 drop 2, this is 8 volts. Okay. And then here we have this voltage here. Let's just check if this is going to be operating. 4K, 1K, 1K, 0. Okay, this is going to be voltage division, right? Oh my god. That's a lot of steps. So 10 gets divided across 1K and the sum of this, so that's 6K. I'm just going to cancel the K for simplicity. So that's going to be 1.6 volts. Now that's interesting because we want to verify this voltage here. This voltage is going to be 1.6 minus 8. That is a negative voltage, clearly less than 0.7. So this one is correct. And this one will have a current of 8 over 3K. That is also clearly greater than 0. Since this is correctly on and this is also correctly off, this is the correct state. What does this imply? Since this 3K holds our output voltage and we know that this is 8 volts, then this is 8 volts. This is our answer. Make sure to leave your verifications here. The partial points are larger when you provide your justifications on your states. Okay, so for this final circuit on diodes, just to test your understanding, I added this extra current source to make it a little more trickier. A good attack here would definitely be nodal analysis. You know, you can never go wrong with nodal analysis, right? I'm gonna duplicate this layer and I'm gonna set this to 0.7. I'm assuming that this diode is gonna be on, so I can just replace this with 0.7, right? Now we need to check if this current is positive. Okay, this is gonna be our condition. Doing nodal analysis here, we should get this current flowing out, and then the 0.7 here, 0.7 over 3. This current is flowing inwards. We need to define what V is later. And then we have the current flowing through here, so that's 0.7 over 5. And then this extra current here, ID, this is all equal to 0, right? Now this voltage here for V was defined as 0.7, right? Okay, so just to speed up on time, I'm just gonna shift solve this. This gives us an ID current of about 0.426, which is clearly greater than 0. So that means this state is correct. Now the question here is going to be, what is this I? I is equal to 0.7 over 3. Sorry, that's just 3. That's going to be 0.233 amperes. This is our answer. Alright, that's it for diodes. Okay, proceeding with BJT analysis, it just extends diode analysis. Let's say we start with cutoff again. Now this is the wrong assumption, but again, the recovery is always very fast. This is 1.2 volts, again, by Ohm's law. If your current here is 0, then your voltage here is also 0. 1.2 minus 0 is 1.2. Now there is enough voltage to turn this diode on, but we said it was off. 1.2 is greater than 0.7, right? It's supposed to be on. This state is wrong. We're going to proceed to FA. Now with FA analysis, this means that this is going to be 1.2. This is 10K. This is 0.7. Ground. Alright. I'm going to use the current source here. I apologize for my bad drawing. That's 1K, this is 10. What is the current flowing through here? That is going to be 10 minus, sorry, it's going to be 1.2 minus 0.7 over 10K. Now to get this, we just take the current here and scale it by 100. Alright, that's the current flowing through here. This one, trivially, IB makes IB greater than 0. And this one, let's try to just calculate this real quick. 1.2 minus 0.7 over 10K. And then I'm just going to multiply this by 100. That's IC is 5 MA. Interesting. What's great about this is the M and the K here cancel by Ohm's law. So that's just going to be 5 volts. 10 drop 5 means V out here is 5 volts. Right? Now let's try to validate if this is correct. We already know that IB is already operating. The next thing that we want to validate here is VCE. VCE is equal to 5 and it is greater than VCE is at. So that means this is also correct. We are operating in forward active and this is our correct answer. To do BJT analysis, this is what a BJT looks like, by the way. It has 3 states. We have cutoff, forward active, and saturation. I'm gonna draw the forward active model here. It has a diode. and then a dependent current source, which depends on this diode. Wait, before I do the checks, do you know what these terminals are called? My mnemonic here is comeback era. CBE. Collector base emitter is comeback era. The main checks here is going to be, first, check this voltage, the BE junction voltage. If VBE is less than the operating voltage, usually 0.7, then immediately you're in cutoff. If it's greater than, you need to be in these two states. Let's say you've disproven that. We need to check this current here. It's called IB. Okay, IB, in both cases, needs to be operating properly. It needs to be positive. If it's negative, you need to be in cutoff. Now, when you are here, how do we differentiate if we are in FA or in saturation? The differentiating factor there will be VCE. CE. If your VCE is greater than VCE sat, which is usually 0.2, this is given value, then you are in FA. Otherwise, you should be in saturation. Right? I have an alternative check for saturation, which is faster for me, and I derived it as IC FA should be greater than IC sat. Okay. I have a derivation for this, and I might put it in the description. So in a nutshell, this is what you need to check. In cutoff, just one state, check if the diode is not conducting. In FA and SAT, verify that the diode conducts properly, and then check the saturation voltage or saturation current. For the models of the other states, in cutoff, you can imagine it as the BJT, I just extracted it out of the circuit. Tinanggal ko lang. At ang saturation naman, isipin mo na at some point, it cannot supply or generate any more current. The diode is still operating, but the current source turned into a voltage source. And this usually is 0.2. It can be 0, it can be 0.2. Check nyo na lang kung ano nasa given. Alright, to proceed with another example, I have here two BJTs. I'm gonna start with assuming both of them are FA. Right? FA. This is gonna be 10K, and I said that this diode is operating, so this is gonna be 0.7. Now these 7s cancel out. There is 1 volt across here, and because of this 10K, this makes it 0.1 MA, flowing like this, right? Now we are going to scale it by 100 since we are in FA. So there is a scale factor of 100 here. That would imply that this current source here is just moving this by 2 decimal places, 10 MA. And then we have the voltage across this one. So that is 1K, 20, and then we also said that this is forward active, right? So this is another 0.7 here. So this is where we want to do nodal analysis. VC minus 20 over 1K plus this current here, VC minus 0.7 over 10K, and this extra 10 MA here. Now this is all equal to 0. I'm gonna do some shift solving real quick. So VC, this voltage here, it is equal to 9.15 volts, right? I can pretty much just discard this part of the solution now. It's not important anymore. What we can verify is this one, the IB here is positive. We'll check that later. IB here is positive. Next is, let's analyze the circuit here. 9.15 gets fed into 10K. This is 0.7 again because of this. So that's I. And then you have this current source here. Okay, this is a little interesting. Watch. All I know is this current here is positive. That's good. I is greater than 0. That's good. And then I'm going to scale it by 100. So this is 845 micro. I'm going to scale this by 100. 84.5 milliamperes. Okay, what does this mean? If this cancels with this is going to be about an 84 voltage drop. 20 minus 84, this means that V out will be negative. So about negative 60 or negative 50 something. All we know is that it is way less than 0.2, right? So this model is not allowed anymore. Since this diode is conducting, again, if the diode is conducting, you're only in 2 states. If it's not FA, you're going to go to saturation, right? So we're going to change this into a 0.2 source. There we go. Now let's verify this. This is no longer 84. It has saturated. This current here is going to be 20 minus 0.2 over 1K. This should give us 1.98 MA. Alright. This is IB. Okay, let's verify that this is in saturation. We need to check if ICFA must be much larger than ICSAT, right? This is our IB. Let's scale this by 100. 100 times 845 micro must be greater than ICSAT of 1.98 M. 100 times 845 micro is 84.5. 84.5 M, which is greater than 98 1.98 M. So this is correct. That means that this is SAT. Sure na tayo dito. How about this one? 9.15 volts across CE is greater than 0.2. So this is gonna be forward active. Okay. So ito yung states natin. Now, ano yung value natin for VO? Since nag-saturate siya, this one, VO here is simply 0.2. Ito yung sagot natin. Alright, to test your understanding, I combined a BJT with a diode. Nice. What's a good starting point? Again, we always start with guesses. I'm gonna assume forward active for this BJT, and then I'm gonna assume this one is on. How do we get IB here? There is no resistor, so we can't use Ohm's law. The next best bet is to use KCL. I'll call this VA. Oh no, instead of VA, we know that this is FA, right? And this is essentially a diode. So it's gonna rise by 0.7 here. Nice. When we do this, we can now do KCL to find this current here. That is going to be 0.7 over 500. That's the current flowing through here. And the current flowing through here is going to be 0.7 minus 5 over 3050. The current flowing through here is this. That's going to be IB. Now we just need to check if this is positive first. 9.83 micro. That is nice. It is greater than 0. So we already know that this is conducting. It can be either saturated or forward active. Now to simplify this a bit, I'm just gonna change this model. I'll change it to forward active, right? From here, we are gonna scale this by times 100 based on this beta. 0.98 MA. This is our current flowing through here. Now we know that this is on, or sorry, we assume that this is on. So its on voltage is gonna be 2 volts. Let's try to do nodal here. We set this to 2, subtract by 5, the current flowing through here. And then the current flowing through this diode, we don't know it yet. We only know that this is 0.93. 0.93 M. And then the current flowing through this diode here, that's going to be ID. We set this all equal to 0. So we have 3 branches of current, these 3 terms. ID is equal to 2017 microamperes, clean number. Now, where do we go from here? We know that ID is positive, so that means this is operating properly. This one is 2 volts. VC is 2, and it's greater than 0.2. And its current is also positive, so this is FA. So this is FA, this is on. Our circuit is correct, but what's being asked here is P out. So just to remind, P is equal to V times I. We know that V is just 2. And our current here is this 2017 micro. So this should give us 4.034 milliwatts. So P is equal to 4.034 milliwatts. And is it absorbed or delivered? We solved our current to be flowing this way, right? And this is the positive terminal. If the head enters the positive terminal, it's absorbed. This is our answer. MOSFETs are like BJTs, but instead of controlling the current, we control the voltage, which is the voltage here. Let's falsely assume that this is cut off. Our VGS is equal to 5.4, and that is clearly greater than 1. From dun pa lang, hindi na pwede ang cutoff natin. So let's go to the next state. I will assume saturation. Using saturation, we have the model 5.4, and our source here will look like this. K over 2, so that's going to be 1M over 2. VGS is 5.4. VTH is 1. And then square this. This is 9.68 microamperes. Yan. We have here a 1 kilo ohm resistor. So this 1K will cancel with this M. This will give us a voltage na 9.68 here. That's 20 to. 20 drop 9.68, 10.32. Yeah. To verify our state, una muna is, alam natin na yung VGS natin is 5.4. That is greater than 1. And ang VGD natin, equal siya sa difference ng 5.4 minus 10.32. This is negative 4.92. And that is way less than 1. Dahil ito yung states natin, tama to. Tama yung saturation. And that means ang ating output voltage is 10.32. When we are doing MOSFET analysis, ito nga pala itsura ng MOSFET by the way. Different siya sa BJT kasi may malaking gap dito. Similar sa BJT, meron siyang tatlong states. Ang cutoff state, no, kasi ilagay ko yung saturation dito, linagay ko yung saturation sa gitna. Very weird, no? Tapos itong third state, I'll call it ohmic. For saturation, ang kanyang model looks like this. Nandiyan pa rin yung current source natin, but instead of putting a diode here, open lang to. Ano tawag sa tatlong terminals na to? Ang mnemonic ko dito is don't go south. DGS, drain gate source, is don't go south. Yan. Chine-check natin dito is, instead of the current, the voltage. If yung gate source voltage natin, hindi umabot sa threshold, kinulang, cut off yung circuit natin, or magka-cut off to. Now, ang next check natin dito is, what if it went this way? Yung gate source natin, lumagpas siya ng VTH. It's gonna be one of these two states. Ano naman differentiating factor natin for this? Ang next i-check natin is yung voltage across this gate drain. VGD, VGD. Tapos comparison ulit with VTH. Now, if same sign siya, ohmic. Kung opposite sign, nasa saturation tayo. Ang itsura na rin naman pala ng mga model dito is, for cut-off, same lang sa BJT, hinatak lang natin sa circuit, tinanggal lang. Sa ohmic naman, ang idea dito is, ang current source natin, hindi na niya kaya mag-supply ng extra current. So, naging resistor na lang siya. Ang value pala natin dito is K over 2 VGS minus VTH squared. Okay, ito yung value natin for saturation current. For ohmic naman, ang value natin dito will be 1, ibahin ko yung kulay. 1 over K VGS minus VTH minus 2. Okay, ang remembering factor ko dito is may 2 ka dito dahil yung saturation, dalawang states nakikita niya kasi nasa gitna siya. So may 2 dito, may 2 dito. So ohmic naman, wala kang 2. Okay, wala kang ilalagay na 2 dito. Kasi isa lang nakikita niya, si SAT. And so, goods pa naman, no? Sige, proceed tayo sa mga examples. How do we analyze a circuit like this? Wala tayong input kaagad. Very weird. Una muna is, ang ating drain is equal to our gate, no? VG is equal to V, D. What can this imply? Kung kinuha natin yung gate drain na, itong gate drain, subtract natin yung VG at VD, makukuha natin, since equal sila, magka-cancel lang sila, di ba? 0. That is clearly less than 1. Ano ang ini-imply nito? Kapag less than 1 siya, nasa saturation tayo. Di ba? So, imposible na mag-ohmic to. Ang only option niya is mag-saturate. So, gagamitin natin ang kanyang saturation model. I'll just match this color. Ayan. Ang K over 2 natin will be 1M over 2. Gate source natin, ayan, hindi siya given. Gawin ko lang siya muna VD. Tapos, subtract ko siya ng VDH natin na 1. So, that's squared. Ngayon, meron tayo ditong 1K resistor. Ayan. And ito, this is VD. Let's do some nodal analysis. VD minus 10 over 1K is this current. And the current here is this. So, equal to 0. Dalawa lang yung current natin. So, nung nag-shift solve ako, dalawa yung nakuha ko dito. VD is equal to negative 4.35 tsaka 4.35. Ano dito yung gagamitin natin? In-assume natin saturation model natin, di ba? Sige, try natin itong negative 4.35. That means, babagsak siya dito sa gate. At ang VGS natin is ito. Compare natin siya dito sa VTH. It is less than 1. Eh, sinabi natin saturation. So, ibig sabihin nun, bawal to. Ito lang yung pwede natin gamitin na VD. So, our VD value here is going to be equal to 4.35. Lalagay ko lang siya dito. Yan. Tagalin ko na to para lang mag-clear up ng space. Delete. Yan. At itong VD na to, magta-translate siya dito sa next circuit natin. What's interesting here is, nag-copy-paste lang ang kanyang voltage, no? Ano pwede natin i-infer dito? Since ito yung value natin ng VD kanina, same lang siya ng current, no? Same lang sila ng current. Interesting. I'm gonna assume na saturate rin to. So this should be 1M over 2. Itong gate source natin, squared. Ano value nito? Sabi ng calcu 5.61 MA to. Alright, we have here a 1K resistor, and this is 10. Now notice na ang K at M dito magka-cancel lang. So this is a 5.6 drop. 10 minus 5.6 is 4.4 volts, no? Let's verify. Alam na natin kanina na imposible to mag-ohmic, no? So, saturated na to. Ito na lang din natin i-check. 4.4 to... Sige, itong 4.35, alam natin na greater than 1 na to. So, that's okay. Ang next na i-check natin is yung difference ng gate versus drain natin, no? 4.35 minus 4.4. This is gonna give us a negative number, no? So, this is less than 1. Dahil less than 1 to, saturated rin to. And nag-match yung model natin dito. So, tama yung circuit natin. That's great. Ang tinatanong dito is, what is Vout? Vout is, ito, nasolve na natin kanina, as 4.4 volts. To test your understanding, pinagsama ko ang BJT at ang MOSFET para lang masanay tayo kung ano yung itsura ng models nila. So, ang conditions ng BJT natin is defined here, and ang conditions ng MOSFET natin is defined here. What's a good starting point? Again, we always guess. I will assume FAC BJT at I will assume na saturated ang ating MOSFET. For BJT, let's draw its model. That is 10K, tapos may 0.7 tayo dito from this terminal, no? This is 60 micro. Now, isi-scale natin siya by 100 to get IC, no? Ang IC natin is times 100 lang nito. So, this is 6 MA. Yan. 10, tas ito 1K. Now, notice na ito, open lang to, di ba? Open lang yan sa MOSFET. So, wala nang current na daan dito. Where does this go? Ang M magka-cancel sa K. This is a 6 volt drop. That means 10 minus 6 will give us 4 volts here. Let's go to this next MOSFET. Yan. Ang value natin dito for SAT is K over 2. So, 1M over 2. Ang ating gate source is 4 minus ang ating threshold squared. This will give us 4.5 MA. Where does this go? Across this 10, meron tayo ditong 1K. Now, ang K magka-cancel ulit sa M. So, this is 4.5 drop. Now, a 10 minus 4.5 drop is equal to 5.5. Let's verify our states. Sinabi natin FA to, di ba? Una muna, isang current natin is positive. That's good. Next, i-check natin ang ating VCE. 4 volts raw ang VCE natin. 4 is greater than 0.2. So, goods. FA tayo. Correcto. I-check natin is yung SAT. Ang gate source natin is 4 and it's greater than threshold na 1. So, goods. Next is i-check natin is gate to drain. 4 minus 5.5 is negative 1.5. And that is less than na threshold na 1. Which means, goods rin to. Saturated rin ang BJT natin. Ang MOSFET natin. Tama ang circuit natin. And ang ating output is 5.5 volts. So, good tayo dito.